Okay, in this example, we're going to look at these four integrals. And what they have in common, they all are rational functions. And in their denominator, if you notice, the highest power of x is to the second. So all of those are called quadratics in the denominator. And we're going to practice how we integrate rational functions in this form, where there's a quadratic in the denominator. And it turns out, actually, we're going to need different techniques for each of these. So this is why we're going to focus on the different ways we'll hit this type of integral. So first, put this on pause and try each of these on your own based on what we've already done in class and what you've already learned in Calc 1. Okay, before we dive into each of these individually, I want to give you the big picture strategy. What you want to try to do is try to factor the denominator. So we're going to see that only two of these denominators are going to be something that we can factor. This one will factor and this one will factor. And this one will factor here into a perfect square. This one will not be a perfect square, and that's going to lead to two different approaches on how we integrate. Now this denominator here, it's kind of already in a factored form. What we're going to notice is that it's in the form of a constant times a variable quantity squared, which should be ringing a bell from the looks in the form of an integral that leads to an inverse trig function. So if you're not remembering what inverse trig function this is going to lead to, you can do a quick recap from that inverse trig video that I made as well. And lastly, that means when you have one like this that we can't factor, we're going to actually complete the square to try to get it into a form that looks similar. It won't be exactly the same, but we want it to look like a constant times a variable term squared, so that we can also basically use the same strategy that we did in B and take advantage of that inverse trig function. So those are some extra hints if you haven't gotten all of these yet. So try them again, and then I'll show you the full solutions on the next slides. Okay, so the first way I generally start these is to try to factor when you have rational functions that you're integrating. So right now that means I'm just going to need to try to factor the denominator. So if you haven't already, put it on pause and see if you can factor that. And you'll notice this is going to factor into a perfect square. It factors into 3x plus 2 squared. So now this is the same as rewriting it as 3x plus 2 to the negative 2 dx. So now our strategy is going to be to do a u substitution. So let's let u be 3x plus 2, and that means that du is going to be 3 dx. And you notice what we have left, we just have dx, so I'm just going to solve for dx. I have 1/3 du is going to be dx, which means I can replace this and rewrite this integral as 1/3 u to the negative 2 du. And then I can just use the reverse power rule for integrals. And notice I have my constant of integration because this is an indefinite integral. And then at the end I'm just going to rewrite this in terms of x like I started with. So notice u to the negative 1 is the same as having 1 over u, but I'm going to replace that u with 3x plus 2, and then I have plus a constant. And I want to note that this is going to be a type of u sub that we want to be able to start to do in our heads in this class. So in general, if you have, say you have this outside function, in this case, this quantity, the negative 2, where it's a familiar outside function, and your inside function is linear like this, which means that your x is only going to be raised to the first power at most, then in general, this integral is just going to be 1 over your antiderivative, and then you just keep the same thing for your argument. So this is assuming that capital F is an antiderivative. So we'll do this in general, and you'll be able to start to do a lot of these u subs in your head that way. Okay, whenever you have a denominator that has this form, so it's 1 plus some quantity involving a variable squared, this should be ringing a bell because it looks a lot like a famous integral from Calc 1 that involves an inverse trig function. So take a second and see if you can remember which one. And if not, there's that nice inverse trig recap video that I have done as well. You can go and check that out. So the short answer is this integral is going to be inverse tangent. And again, we proved that in that other video. I'm just putting it in both forms. We'll either say arctan or inverse tangent. That's equivalent. So what we really have here is we don't have it quite in that form, but we will after we do a u substitution. So let's let this quantity in here be my u, and then just like last time, my du is 3 dx, which means I can rewrite this integral as 1/3 du over 1 plus u squared. And this we know is just going to be 1/3 times arctan or inverse tangent of u. And then I'm going to replace u at the end. So this is going to be 1/3 arctan of 3x plus 2 plus a constant. And again, this one's in that form that I mentioned previously where we could start to do this in our head because my outside function is really this 1 over 1 plus u squared and my inside function is linear. So then we realize we're just going to need to find the antiderivative and then multiply it by that 1/3 factor out front. Okay, so this one, you'll notice if you try to factor the denominator, it won't factor. So our strategy is we want to complete the square in the denominator so that we can get this in the form where I have 1 plus some quantity squared, because then we know exactly how to integrate this. That's just going to be my inverse tangent. So we're going to complete the square in order to get this term. And we're going to have to do some algebra and factoring in order to get a 1, because as you can see, I don't have a 1 here. Right now I have a 7. And I also don't have a perfect square here. So this one, I'm going to warn you, is really messy algebraically, but I did that on purpose so we could kind of see a worst case scenario. And if you can deal with this one, you'll be fine with any of these other ones where you have to complete the square. Okay, so just a refresher of how you complete the square when you have a quadratic of this form. And the idea is that I want to figure out what I need to add and subtract. So I'm going to take some same term, add and subtract, so that I don't change my overall value or my overall expression. And I would like this piece then to be something that I could factor into a perfect square, and then this is going to be my remaining constant. So before I do this, you have to be really careful using, there's a little rule you probably learned in high school where you take your coefficient of x, divide it by 2, and square it. And that's true, but you can only do that if your original coefficient of x squared here is just 1. So you need to factor out anything that you have in front of your x squared. So I'm going to factor that out here. And then you don't have to worry about factoring it out of this little extra term here, the 7, because that's just going to be kind of my leftover constant that I get. But you do need to make sure you factor it out of the terms that involve x. Okay, so now let's see, what am I going to add and subtract? So now you take the coefficient of x, divide it by 2, so that's going to give me 6 over 9, or 2/3. And then we're going to square that, which is going to give me 4/9. And so I'm going to add and subtract 4/9 here. And then I can just simplify. So now I'm going to get 9. And this piece right here has now become a perfect square. This is going to be x plus 2/3 quantity squared. That's what's there. And then this piece here is just my leftover constant. But notice you have to make sure you multiply the 9 through here. So really I have -4 plus 7, or 3. Now, as you recall, I want to get it into this form, so I'm not quite there yet. This is looking kind of close to a quantity squared, but this is not 1. So I'm now going to factor out 3 from both terms. Okay, and then I'm going to have left this 3. And then when I factored out the 3 there. So now this is looking good, but basically I need to rewrite this so it's an entire quantity that's squared. So notice this is the same as if I just took this quantity here and multiplied both terms by the square root of 3. So this would look like 2 square root of 3 over 3, quantity squared, and then plus 1. Okay, so now I have this in a nice form finally, where I can think of this whole thing as my u, and then the integral is going to fall out pretty quickly from here. So it's basically a lot of messy algebra in order to get this in the form where we have the denominator like this. So let's rewrite this. So notice right here, this 3 that's out front, because this whole thing is in my denominator, I can pull out the 1/3, and then my integral that I'll have now is going to be square root of 3x plus 2 square root 3 over 3 all squared, and then plus 1 dx. So now it looks like the form on the previous page. We're going to let this be u. And notice this is still linear. It's just that my coefficient is square root of 3 now. And so that's going to be what comes out front. So I'll have 1 over 3, and I'm also going to have the square root of 3 now. And then the integral of du over u squared plus 1. Okay, so now we know that it's just going to be 1 over 3 root 3 inverse tangent of this entire u. So let's make some more space. And this is what we end up with. Okay, and then lastly, what happens if we can factor the denominator, but it's not a perfect square? So notice when we factor this one, you're going to be able to factor it into 3x minus 2 times 3x plus 1. All right, now this is going to require a technique called partial fractions. So we're going to get to this in section 6.3. So the general strategy is that we're going to rewrite this as some constant over 3x minus 2 plus another constant over 3x plus 1. This just comes from what we understand about how we add fractions that don't have the exact same denominator. And so we realize that we should be able to decompose a rational function of this form into a sum like this. And the goal of this is integrating things in this form is going to be much easier than trying to integrate it when it's over here. So now we're just going to try to solve for what a and b have to be. And you do this by multiplying both sides through by this denominator. So notice if I multiply the left side of the equation through by this denominator, then I'm just going to be left with the numerator. And if I multiply this term through by 3x minus 2 times 3x plus 1, the 3x minus 2's are going to cancel, and I'm just going to be left with 3x plus 1. And then same thing when I multiply this term through by 3x minus 2 times 3x plus 1, I will be left with b times 3x minus 2, because the other ones are going to cancel. And now I'm going to solve for a and b, and a nice way to do that is, since this has to hold for all x, we'll pick an x value that's going to make this term 0. So notice, when x is negative 1/3, this whole equation is going to become this whole term will become 0, and then I'll have b, if I plug in negative 1/3, I will get negative 3 here, which is going to tell me that b is going to be negative 1/3. And then we can do the same thing. Let's try to make this term be 0. So notice when x is 2/3, this whole equation is going to become 1 is a times positive 3 and then plus 0. So that's telling me that a is going to be positive 1/3. And so I can come back up here and rewrite this here as positive 1/3, and this is negative 1/3. And then it will make my integration much easier. So this is 1/3. Because now you can basically notice we're trying to do this integral, and that's going to be the same as doing this integral minus this integral. So let's give us some space. And as you're noticing, here's one where we can again do our u sub in our head. I can pull out this 1/3, and then I have the integral of 1 over 3x minus 2. But this is linear, so this is going to be the same as I'm going to have 1 over this coefficient, and then the natural log of my denominator, 3x minus 2. So that's that term. And then this term here, I'll have minus, and it'll be the same idea, 1/3. So I'm just doing the u subs in my head here based on what we've practiced earlier. And then I'll have plus a constant. And so this can all be simplified just using what we know about properties of logs. And that's it.